Two large family members have decided to enter into an alliance by marriage. The first family has 7 men, and the second has 7 women. The ages of the two family members match up. The families insist that everyone must marry someone either their own age or someone one position younger or older. The graph representing agreeable marriages looks like the graph below. Notice how we have a bipartite graph, and a possible marriage arrangement for all the men and women would be a matching. The first question is, how many marriage arrangements are possible if exactly 4 men marry women not their own age? Let's think of this in terms of x's and i's, where if we make an x on the graph, we have 2 men marrying women not their own age, and if we have an I, we have a man and woman marrying that are the same age. So because we want the number of arrangements that are possible if exactly 4 men marry women not their own age, we would have 2 x's and 3 i's. For example, one possible arrangement would look like this. There's 2 men marrying someone not their own age, and here's 2 more men marrying someone not their own age. Here we have exactly 4 men marrying women not their own age. The remaining 3 couples marry someone their own age. So every possible arrangement in which exactly 4 men marry women not their own age, we would have to have 2 x's and 3 i's. Which means to answer this question, we need to determine how many permutations we can make with 2 x's and 3 i's. Which brings us to the formula for the number of permutations or arrangements when order matters of n objects when we have n sub 1, n sub 2 through n sub k indistinguishable objects. The number of permutations is equal to n factorial divided by the product of n sub 1 factorial, n sub 2 factorial, all the way to n sub k factorial. So in our case, the number of permutations of 2 x's and 3 i's would be 5 factorial, the number of objects, and then divided by, because we have 2 x's and 3 i's, we divide by the product of 2 factorial and 3 factorial. Simplifying, we have 5 factorial, which is equal to 5 times 4 times 3 factorial, divided by the product of 2 factorial and 3 factorial, which is equal to 2 times 1 times 3 factorial. Simplifying, 3 factorial divided by itself simplifies to 1, 4 divided by 2 simplifies to 2, 5 times 2 is equal to 10. There are 10 possible marriage arrangements under this condition. And the second question, how many total marriage arrangements for 7 men and 7 women, given the only condition is everyone must marry someone their own age or someone one position younger or older? This is a much more complicated question. To help us answer this question, we will look at several cases of smaller family sizes and determine the possible number of marriage arrangements. So going to the next slide, I've already set a lot of this up. We have a family size of 1, a family size of 2, a family size of 3, a family size of 4. We'll also look at a family size of 5. To determine the number of arrangements, it'll be easier to think of this as determining how many permutations we can make using x's and or i's. So for a family size of 1, of course, there's only one possible arrangement. Let's record that in the table. For a family size of 2, we could have 2 i's, meaning the men and women marry someone their own age, or we could have 1x when the men and women don't marry someone their own age. These are the only 2 possible marriage arrangements. Let's record the 2 and move on. And again, thinking of this in terms of x's and i's is probably easier. So we could have 3 i's for a family size of 3. We could have an I and an x. We could also have an x and an I. There are no other possible arrangements. We have a total of 3 arrangements. Notice so far the family size matches the number of marriage arrangements. Let's see if that continues. Next we have a family size of 4. We could have 4 i's. Next we could have 2 i's and an x. Or we could have an I, an x and an I. We could also have an x, an I and an I, or 2 x's. These are all the possible arrangements. Notice here we have a total of 5 possible marriage arrangements. So notice now the family size is not the same as the number of arrangements. Again, our goal here is to look for a pattern in the number of arrangements. Let's take a look at the family size of 5 on the next slide. Let's start with 5 i's. Next, let's use 1, 2, 3 i's and an x. And now let's move the x around. Let's use the arrangement of I, xi. And now let's use I, xii. And now let's move the x to the first position. We have x, I. And now let's try using two x's. We have x, I. We can have x, x. Or we can have I, x. And now we're done. There are no other arrangements. We have a total of 1, 2, 3, 4, 5, 6, 7, 8. So looking at the number of arrangements, we have 1, 2, 3, 5, 8. This should remind us of the Fibonacci sequence. Notice 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. Let's take this sequence back to the first slide. Again, we have 1, 2, 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, 13 plus 21 is 34, and so on. But remember, 1 was the number of arrangements for family size 1. We'll call the first term a sub 1, then we have a sub 2, a sub 3, a sub 4, a sub 5, and so on. Remember, we're looking for the number of arrangements when there are 7 men and 7 women, which would be a sub 7, which is 21. There are 21 possible marriage arrangements. And finally, we're asked to give a recurrence relation that fits this problem. We'll define the number of arrangements. We add the previous two terms in the sequence. So if a sub n is the number of marriage arrangements, a sub n is equal to a sub n minus 1, the term right before a sub n, and then plus the term before a sub n minus 1 is a sub n minus 2. I hope you found this helpful.